All right, here we go. Talk a little bit about your simple circuits that you made and the rules, and then we'll talk about current as well. Okay, so the simple circuit that you made, here's what I'm claiming is my simple circuit. I may not necessarily need this switch. In fact, I don't, but I'm just using it for convenience's sake. So, and I'll close the switch though, and hey, there we go. There's a circuit that works. There's a circuit that works. Yay, circuit works. And this is, aside from the switch, pretty much the simplest circuit I can get. So let's look at the components of this. What kind of rules are necessary? Well, one thing I definitely need a source of energy, and that's what the battery provides. So I need a source of energy. Notice it's not providing the charge though. The battery doesn't provide the charges. See the charges in the wires here? See the charges in the wires? I'm going to go back here really quickly. If I pull out any wire, the wire's already got the electrons, the charges inside of it. Anything has charges inside of it, and a wire is typically made out of a good conductor, and so that's why the charges are allowed to move. The battery doesn't provide the charges. All the battery's doing is providing the push. Once I do this, the battery starts pushing the electrons, and they all start pushing each other around like that. So next up, though, are the electrons itself, or the material here that's allowing the electrons to move. So I need basically a conductor or a source of charge. So a conductor or source of charge. It's like if you had a river, you need water for the river, but you'd also need to have it at some height in order to allow the river to flow. So that's kind of like that stuff right here, and that's over there. Okay, and then the last thing that I would need is this right here, which is what we call a resistor. So I need a resistor. And yes, a light bulb is a resistor, even though this particular resistor is producing light. Some resistors just resist current. That's all that they do. We'll talk about resistors in a moment or a little bit later. Okay, so and the reason why I need the resistor, because you can see if I took the light bulb away and just connected this, I get not a really good working circuit. I blow up my battery and, you know, I get battery acid all over my face, and that's not what anybody wants, I don't think. I'm not 100% sure. So yeah, I need a resistor in there in order to control the current, so I don't want too much energy too quickly, and that works right there. So I need a resistor of some sort as well. There's one last thing that I need, and it's a hint right there with my switch, is I need it to be a closed loop. If my circuit isn't a closed loop, then I'm not, so that's the last thing I need, is a closed loop. Because if the circuit isn't a closed loop, it's not gonna flow. So if I just did, you know, something like that, that's just not gonna work. It needs to be a closed loop. All right. So that being said, let's move on to current really quickly. So current. Once again, I see my electrons in the wire, but they're not flowing yet. Once they flow, that's what we call current. You can kind of think of like a water flowing in a river. We call that current as well. So current, when we talk about circuits, is the flow of charge. Current is the flow of charge. So you can see the electrons, they're moving around. They go from the negative terminal of the battery, and they go all the way down to the positive terminal of the battery inside the circuit. And we call that current. Yay. Okay. Now, really quickly here, what charges do you see moving? Yeah, that's right. It's the electrons. The electrons are the charges that actually move. However, there's a little section up here. It says show current, electrons, or conventional current. I'm going to switch it now to the conventional current. And you can see the charges go in the opposite directions. Electrons are moving clockwise around this circuit. The conventional circuit goes counterclockwise. Here's the deal. We end up using conventional current, which is essentially the imagined flow of positive charge. Really, it's the electrons that move inside of a wire that we're going to use in this class, but you can thank Ben Franklin for this one. It turns out that, conventional current is the imagined flow of positive charge. Ben Franklin, when doing experiments, was basically saying, oh, it's the positive charge that flows from the positive terminal of the battery to the negative terminal. And then we found out later, oh, crap, it actually ended up being the electrons. But we still use conventional current, so that's what we're going to use here. So conventional current, goes from the positive terminal of the battery to the negative terminal of the battery. So I'm going to cut this really quickly. So current here, basically the battery produces an electric field. The electric field inside the wire pushes the charges to the right. Here, again, these are positive charges, I know, even though it's not the positive charges that actually flow. Sorry. But yes, it produces a current. And yes, this is the symbol we use, capital I. So capital I. So the symbol we use for current is capital I. And if I were to, let's see, I'll go back here really quickly. If I were to take this little marker, I say this marker right here, and I go from there, I'm going to count the amount of charge that flows by in a certain amount of time. That's essentially what current is. How much charge, the amount of charge, divided by the amount of time, the rate, that's the rate, divided by the change in time. So yes, the amount of charge over the change in time. Well, okay, so if I did in like 10 seconds, I'm going to count the amount of charges that I see in 10 seconds. All right, here we go. Then I started going, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 40 coulombs of charge. I just counted 40 coulombs of charge. How did I do it? I'm amazing. And then I do it in 10 seconds. Well, then I would get 4 coulombs per second. Coulombs per second. And that is the current. It's 4 coulombs per second. However, nobody uses coulombs per second. We don't use coulombs per second. So coulombs per second. We don't use coulombs per second. Instead, we actually use what's called ampere. I think there's an accent aigu right there too. Ampere by this guy, ampere. So we say instead of, what did I get before? 10, right? No, 4. So we say 4 ampere. Except, of course, nobody says ampere either because we've Americanized it since then. And we go, you know what? Instead of ampere, we're going to say amps. A-M-P-S, amps. So 4 amps. That's what we use instead, amps. From the French, ampere to amps. That's what we use. So amps is the unit of current. So current, again, the symbol is capital I. It's the imagined flow of positive charge. Even though it's actually the electrons that move. Sorry. And then the equation we use. Whoa, that's interesting. Well, at least we got that. So we got this right here as well. The equation we use, pretty simple equation. So the current is equal to the amount of charge divided by the change in time. Or if you're in calculus, dq dt. So that's kind of the equation we use. And there you go. Yeah. So really quickly, see if you can figure this out. So for every minute, 120 coulombs of charge flows through this cross section of wire. So it's that little sliver of wire right there. So 120 coulombs of charge in every minute. So how would you calculate the current? I'm going to go ahead, pause, see if you can answer the question. 1, 2, 3. Okay, here we go. So, well, it's the amount of charge divided by the change in time. So the amount of charge they're saying is 120 coulombs divided by the minute. Well, there's 60 seconds in a minute. And that's going to give me 2 coulombs per second. But again, nobody uses coulombs per second. We use amps. So our answer is D. All right. So go ahead and keep doing that activity. Bye.